Welcome back. Let's jump back in here talking about equilibria. And specifically, we are going to learn about today the equilibrium constant and where we get that from. So in the last video, we talked about how equilibrias are created when we have a forward reaction and a reverse reaction that are at equal and opposite rates. So we have the forward reaction happening and we have the reverse reaction happening, and because they're happening at exactly the same speed, there's no overall change in the concentrations of anything in the reaction mixture. So we're going to take a little bit closer look at that here. So we have a reaction that's happening. Specifically here we have N2O4 is reacting, is decomposing to make a 2NO2, and the rate law for this is just the rate is equal to Kf, the F here stands for forward, times the concentration of N2O4. So this is the forward reaction, and so this this equation here describes the rate for that forward reaction. The reverse reaction is just the forward reaction, as the name implies, in reverse. So we have 2NO2 going to N2O4, and this is a single step process here, and so the rate law is just the two reactants plugged into the rate law. And the K sub R here is just K for reverse. So we don't really care exactly what this numeric value is. We just know that it's a constant. That's the main thing. So if we're at equilibrium, by definition, what that means is that the rate for the forward reaction is equal to the rate for the reverse reaction. And since we know what each of these are equal to, because we had both of them back here, rate for the reverse is equal to this, rate for the forward is equal to this, we can set those equal to each other as well. So if we do that, notice we have two different constants and we have two different things that are concentrations. Technically three, I guess, since that's squared. But anyway, we have concentrations and we have constants. So if we rearrange these so that all of the constants are together and all of the concentrations are together, we get this. And since these two are both a constant divided by another constant is just another constant. And so instead of keeping those separate, we're going to combine that together to give us what we call our equilibrium constant. And the equilibrium constant is equal to the products divided by the reactants. And that is always going to be the case. The equilibrium constant is equal to the products raised to their coefficients divided by the reactants raised to their coefficients. In this case, we had NO2, and it had a coefficient of 2 in the equation, and so the NO2 is raised to the second, and the N2O4 is just N2O4. And so it is left as just a single N2O4. So this K is equal to products divided by reactants. It's going to be something we are going to use again and again and again and again over the next couple chapters. This is really the foundational, it's not even really an equation, but I guess it's an equation that we're going to use and build upon for the next couple chapters, this equilibrium constant. Now, I do note down here, it is a little bit frustrating that we use K for this constant. Not only that, there are going to be about 3 or 4 different Ks that we're going to use here. So sometimes people just use capital K. That's not quite as common. KEQ is actually the way that I learned it. When I was taught this, I was taught to use KEQ for the equilibrium constant, EQ obviously being equilibrium. But nowadays, it's more common to see KC. So KC, the C would be standing for like the equilibrium constant using concentrations. There's also a Kp that we will see later on. There's also a Ka and a Kb and a Ksp. And all of these are the same overall equation, products over reactants. It's just each of these have their own little niche use. So A is for acids, B is for bases, Sp is for solubility products, P is for pressure of a gas. So we have all these different Ks that we use. So it's just going to be a little bit of a pain to keep track of what's what. Usually, though, we're going to use Kc in this chapter anyway. In the next chapter, the most common one we'll use will be Ka. And then in the one after that, it will be Ksp. So I just wanted to make you aware of that now, that sometimes it can be confusing because, especially if you go and look in other sources, they might use a slightly different naming method for these. And K is just used for all kinds of stuff. K is by far the most common letter in any chemistry equation or something like that, because not only do you have K used for the equilibrium constant, but it's also used for Kelvin, and it's used for the rate constant, which is related to the equilibrium constant. It's just, there's K's all over the place. Anyway, moving on from that, just a quick note here about what is happening at equilibrium before we close up this video. It's important to remember that at equilibrium, the concentrations of reactants and products are not changing, but this does not mean that they are equal. Now, at the beginning of this chapter, in that first video, I did make a point of saying that we started with equal numbers of cars on the two sides of the bridge, and then we had equal numbers of cars going in opposite directions, but that doesn't have to be the case. So we could have a lot more cars on one side and fewer cars on the other side, but as long as we still had the same number of cars going in both directions, we're still going to maintain the same equilibrium. It's still going to have the same number of cars on each side. So we do not have to have equal numbers of molecules or concentrations on the two sides of the reaction. We just can't have those reactions changing, or the concentrations changing. And the truth is, almost never are they equal. They will practically always have different concentrations because one reaction will be more favored versus the other. So, the concentrations are not equal. The reverse reactions and the forward reaction is still occurring. At equilibrium, the reaction does not stop. For the equilibrium to occur, neither the reactants nor the products can escape from the system. So if, for example, we have a reaction that is occurring in a solution, and one of the products is a gas, if that gas is escaping, well then you're never going to reach equilibrium. Because for the reverse reaction to take place, that gas has to be there to react. And so if the reactant is, if you have a reactant escaping, or if you have a product escaping, you're never going to reach equilibrium. So the reactants and products have to be kept where they can still undergo reactions. They can't be allowed to escape. And then the last bit there, at equilibrium, a particular ratio of concentrations, concentration terms equals a constant, which is what we were just talking about back here. There will be some constant value for that reaction at that temperature, because temperature does have an effect. There will be some constant value that will always equal the concentration of products over reactants. And it does not matter whether you start a reaction with only reactants or products, as long as you have either every reactant or every product. In both cases, you're always going to reach the same equilibrium. Now, you might have slightly different concentrations. So here, this the way the graph works out, you know, the H2 and the NH3 and the N2, they're all, you know, they all end up at exactly the same point here. That doesn't actually have have to happen. You don't have to have the exact same concentrations. You just have to have the same ratio. So the ratio will end up still working out to the same constant. But the concentrations themselves don't have to be exactly the same, no matter where you start. But the ratio will always end up being exactly the same, no matter where you start. So here we have a starting point with just reactants, no product, and we get to this ratio of concentrations, and in this case here, we start with only a product. And the product over time breaks down. It goes back to being reactants. And you end up at the exact same ratio once again. So we don't actually care where we start, as long as we have everything that we need for either the forward or reverse reaction, we will reach equilibrium. Alright, I think we'll call it there for this one. In the next one we will do some practice writing some equilibrium constants. But this is a good spot to call it for this video, so I will see you all in the next one.